Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3, just a little bit later than I had hoped that I would get it to you, but this is yet another attempt on my part to make the whole ensemble concept a little bit more understandable. I don't know whether or not I'll be successful at that, but we're going to give it our best shot here. So let's go on ahead here and take a look at the first slide. And this is in a sense, taking a look at two specific, what I call isobars in the upper atmosphere. They're technically called 500 millibar heights, but they're the equivalent of isobars at the surface. And I don't know how well you can actually see this, but take, for instance, that red line that goes across Baja California, across northern Mexico, and then up across Texas and Ohio and up into the Northeast. Believe it or not, there are 30 different lines almost on top of each other that make up that red area that you see there. And so the idea is that we cannot observe the atmosphere perfectly. We don't have enough observations to do that. So there's always inherent error in any analysis on which a model forecast is based. And sometimes the atmosphere is very, very sensitive to those very, very small errors. And so what we do, or what the folks that do the modeling do, is that they change or perturb, if you will, the initial conditions or the analysis to 30 different extents, but they're very, very small perturbations or changes, okay? As evidenced by this picture here where they're so much on top of each other you can't even barely tell. But again, sometimes the atmosphere is very sensitive to very, very small changes at the beginning. And so this is one of the purposes of ensembles, is to be able to quantify the amount of uncertainty. In other words, if those small changes end up having a huge impact in the solutions 5 or 6 days down the road, then if the solutions are all over the place, you have low confidence in your forecast. And if they're very similar, then you have high confidence. So it's a way to quantify the amount of uncertainty. Okay, so here is what we call a normal distribution curve. And think about a classroom where a bunch of students are taking a test, and these are the test scores that come out. And so if we take a look at the mean here, it's slightly over 48, okay? And then I talk a lot about the 25th to the 75th percentile as being where the majority of the values are located, or at least the middle 50%. And so the green shaded area indicates the 25th to the 75th percentile. Then the edge of the orange, the other edge of the orange, is the 10th to the 90th percentile. And then you have the outliers in red, the extreme values on either end. And so what we're interested in a lot of times is that middle 50%, from the 25th to the 75th percentile. And depending on how widely distributed the solutions are, it may be a narrow bell curve or it may be a fat bell curve, okay? And that just all depends on how much variance there is in the various, in this case, test scores, or in the weather case, solutions. So here is an example of temperature forecast from the European deterministic forecast. In other words, the European model, the operational model, one solution, as opposed to the ensemble mean of all 51 ensemble members. And you can see that there was a huge jump from a 10-day forecast to a 9.5-day forecast, from 46 to 60. And basically, you see more changes. In fact, the third and the fourth column there are how much changes there were from model cycle to model cycle from the deterministic model, and also how that occurred with the ensemble mean. And you can see that the average model cycle run-to-run change for the deterministic was 4.4, and for the ensemble mean, it was only 1.4. So you're going to get less of this knee-jerk change from run to run if you're looking at the ensemble mean, because you're taking a look at all possible solutions as opposed to just one that you're locked into, be it right or wrong. And then if we take a look at the GFS, the American model, and its ensemble, Again, the ensemble run-to-run change is only 1.6, whereas the deterministic change is 4. So again, you're not going to see these wild run-to-run fluctuations. And by the way, in terms of a snow forecast, there was one run of the GFS 2 days ago that had over a half a foot of snow in Raleigh 12 days out, and the very next run had absolutely nothing, and all subsequent runs have had absolutely nothing. So if you were to hear somebody go off on that and say, oh, you know, we're going to get clobbered in 12 days, and then 12 hours later, when the next model cycle run comes out, they're sitting there going, oh, gee, sorry about that. And this is what you don't get by looking at ensembles, is that it's basically taking a look at all possible solutions as opposed to locking yourself in to just one. All right, there are the credits. I hope that makes a little bit of sense. I've always had a fear about this where we didn't use the word uncertainty back before ensembles came along. And so my fear has always been that people are saying, oh, you didn't used to use the word uncertainty, now you are, so you've taken a step backwards. That's not the case at all. This is a huge technological advancement in the sense that we now can quantify the uncertainty, whereas before we didn't know what we didn't know. We were simply locked into whatever model we picked for the day, and some of that was based on experience, granted, but it really sort of locked you in to a solution, right or wrong, whereas with the ensembles we can actually look at just about all possible solutions and quantify how uncertain or certain or confident or unconfident that we are in our forecast. And I think that's useful information to the public, and I hope you do as well. Okay, that is it for now. That's bonus weather video number 3 for this week. The next one will be coming up on Monday. Next daily weather update coming up on Monday as well. You all take care, folks. We'll talk to you soon. See you later. Have a good weekend and enjoy the Super Bowl, no matter who you're for.